In this lesson, we're going to take a look at compound interest. Compound interest happens anytime that you either borrow or invest money, and it's specifically called compound interest because it compounds or builds upon previously built interest. So simple interest, which is something that is simpler mathematically but not really used in the real world, is just when you get a certain percentage every year or every whatever month, week of your original investment as interest. Compound interest does basically that idea, but then it adds to your original amount once you've earned some interest. And then for the next amount of interest, you get earnings on both the original you put in and the previously made interest. Anyway, because of this compounding, we're going to get basically amount of money that's going to increase exponentially, which is great if you've got an investment and not so good if you're borrowing money. Now, because it is an exponential thing, we're going to be using something that looks a lot like the exponential equations that we've already seen. You probably recall that an exponential function is of that basic form where a is the starting amount and the b is the base on which we're going to increase every time x increases by 1. So for instance, if we have this simple equation f at x equals 5 times 2 to the x, we can see that f at 0 is equal to 5 times 2 to the 0, which is 5 times 1, or just 5. So 5 is our starting amount. And then when we put in f equals 1, we get 5 times 2 to the 1. 5 times 2 is 10. So basically our amount of 5 doubled as x increased by 1. And when we go up to 2, it'll double again to 20, and so on. When we go to 3, it'll be 2 cubed, which is 8. 8 times 5 is 40, but that's just the same thing as doubling the 20, doubling the 40, and then we'll stop here, I think, doubling the 80. So that's basically what exponential functions do. And in this lesson, we're going to see how we can use that to solve mathematical problems involving compound interest. So our general form for a compound interest equation is going to look like this. And I will admit that it looks a little bit worse than the simple exponential function, but it actually is exactly the same format. The FV and PV are actually single variables, despite the fact that they're two letters. And what it says is that the future amount that I'll have, or the future value of my investment, or the amount that I will owe, is equal to the present value, so how much the money is worth now, times some base to the exponent n, where n is the number of compounds, or the number of times that we build interest. And even though the base is actually, again, two variables, 1 plus I, all this is saying is that whatever our interest is, we add it to 1. The 1 gives us back our original amount because we still get to keep what we invested or borrowed. And the interest builds on top of that. So for instance, if interest was 20%, I would be 0.2. Our base would be 1.2. Every time we let a compound period pass, we multiply our amount of money by 1.2. Okay, so rather than spend too much time on this, let's jump into an example. And what I'd like to do is, in all of these really, is to start off by basically making a list of things that we know and things that we want. So I'll just leave that original equation on the screen so that we can see it. And in this question, we plan on investing $500 for 3 years at 9% per year. And we want to find out the amount that we'll have if we compounded our money every month. So here we have monthly compounding instead of kind of default, which would be annual compounding. All right, so we'll start off with the easy stuff. The amount that we're investing is $500. Well, that's how much money that we're putting into it right now. So that's going to be our present value. And ultimately, we want to know how much we're going to have at the end. That means that we don't know our future value. That's the thing we're trying to find out. So I'm still going to list it there. I'm just going to put a question mark beside it because I don't know what its value is going to be. Now our I, or interest rate, most people think of interest rates as being per year, but we're actually going to do them, if we look back up at the equation, as interest rate per compound period. And same thing is n. N isn't the number of years we're doing it, it's the number of compound periods we do it for. So in this particular case, we're compounding money every month. So what we do is we take our annual interest rate of 9% and we divide it by 12. so that we can figure out our interest rate per month. So all I do now is into my calculator, I punch in 9% or 9 divided by 100 and then divide that by 12. And when I do that, 9 divided by 100 divided by 12 gives me 0.0075. Okay, and then n is the number of compound periods. And really what this is saying is how many months are there, since the month is the compound period, how many months are there in 3 years? Well, that's just going to be 3 times 12, which is 36. So if you think of kind of the starting point for I and N as the interest rate per year and the number of years, and then you either divide for the I or multiply the N by the number of times you compound in any single year. So every month for 3 years is 36 months. And if our interest rate is 9% for the entire year, it's only going to be 0.75% per month, or 0.0075. And then from there, we just punch it into our equation. So future value equals present value times 1 plus I to the exponent n. Future value, I don't know what that is, so I'm going to leave it as future value. Present value is 500. And this part, usually we do this in our heads because it's a really easy number to do. 1 plus 0.0075 without even using a calculator is 1.0075. And our n is 36. At this point, you got to pull out your calculator. And I will point out that BEDMAS says you've got to do brackets first, which we just did. We did the bracket of 1 plus I. So we've already completed that part. And now we need to do the exponent before the multiplication. So when you're punching this in, don't punch in 500 times 1.0075 to the exponent 36. Some calculators may assume you want to multiply the 500 by the 1.0075 first and then put that answer to the exponent 36. So the way I'd punch this into my calculator is that to the exponent 36. I'd hit the equals button then. And when I've hit the equals button, I'll get out some number, and then I'm going to multiply that by 500. Either way, if you're getting the right answers, you're doing it correctly. Different calculators handle BEDMAS differently, so you do it however works for you. But if you're getting the wrong answers or different answers that I'm showing, try doing it a different way. And if you're getting them right, I don't really care what order you punch stuff into your calculator. Anyway, when you do punch that in correctly, you should get out $654.32, at least when I round to the closest penny. Okay, so that just says if I invest $500 for 3 years at 9% a year, compounded monthly, I'll end up in 3 years with $654.32. Not too bad. All right. For example 2, Greg invests $3,000 for 20 years at 10.4% a year, compounded weekly. How much will he have? So similar to the last one, we know that our present value, the amount that we're investing now, or at least the amount Greg's investing now, is $3,000. And the future value is what we want to know. We don't know how much Greg's going to have 20 years from now. Hopefully a decent amount. 20 years is a long time to invest money. Okay, our interest rate, I, is 10.4% a year, but since we are compounding weekly, we want to make sure that we divide our our 10.4% by 52, the number of weeks in a year. And you will notice some of these questions that, like, why did I do 10.4% instead of just an even 10%? Wouldn't that be nicer? And the answer is actually no. I picked these numbers very specifically so that I get a nice number when I divide by 52. Now, unfortunately, in real life, the numbers are what the numbers are, but I'll do my best to make your lives as easy as possible in these questions. Okay, so once I've done that, I take 10.4 into my calculator. I divide it by 100 to deal with the percent, to get 0.104, and then I divide that by 52, and when I do that, I get 0.002. Okay, that's pretty nice. And by the way, that's exact. I didn't round off or anything. Again, specifically kind of chose that number to work out that way. Okay, and finally, n, the number of compound periods, is really just saying how many weeks are there in 20 years. So 20 years times 52 weeks per year gives us 1,040 weeks. So that's the number of times our compounding will occur. We'll start off with the equation again. It's off the screen, but that's okay. I remember future value equals present value times 1 plus I to the exponent n. And for us, that's going to be 3,000. Again, I kind of do the bracket all at once when I plug the number in because it's easy to add 1 to a number. So that'll be 1.002 to the exponent 1040. So what's happening is our I gets smaller when we compound more often, but our n gets bigger. So we have a smaller base, but a bigger exponent. They kind of cancel each other out. Not exactly, which is why we do this method, but approximately. Okay, same thing. When I punch that into my calculator, you're going to do the 1.002 to the exponent 1040 first, because you have to do the exponent first, and then do the multiply by 300 or 3,000 after. And when you do that, you should get out $23,963.58. Okay, given that your initial investment was only $3,000, this is almost 8 times as much. That seems pretty decent. So investment does make a big deal over a longer period of time. Now, for most of our compounding, we're going to do them either monthly or weekly, but we could do them in other things too. We could do compounding per day or per hour or per whatever we want. A few of them they're ones that people aren't usually familiar with, but they are ones that are fairly common when it comes to actual calculations. Are semi-annual compoundings. Semi-annual, same as a semicircle is half of a circle. Semi-annual is half a year. So this compounds every 6 months or twice a year. Quarterly, as you would expect, happens 4 times a year. And biweekly means every other week. So if there's 52 weeks in a year, there's 26 pairs of weeks. So we would compound 26 times for biweekly. And that one's fairly common. A lot of people get paid biweekly, meaning they get paid every other week. And if you get paid every other week and you're investing money or borrowing money, you tend to make payments at that time, which means that biweekly investments are actually very, very common. Okay, for example 4, Chantel borrows $1,200 for 7 years at 20% a year, compounded quarterly. How much does she owe at the end of that should say 7 years. Let's do 7 years for that one. Can't stand inconsistent questions. Actually, you know what? I think I lied on that one. Let's actually do it for 8 years. We'll change the first number to an 8. I think it works out nicer. Definitely covers up nicer. Anyway, Chantel borrows $1,200 for 8 years, 20% a year, compounded quarterly. How much does she owe at the end of the 8 years? I will point out that 20% may seem like a fairly decent amount or a fairly high percentage. You'll notice that the borrowing percentages are always going to be higher than the investing percentages. 20% is pretty typical of what you'd see for a credit card. So this might be a credit card debt. She decides to buy something for $1,200 on a credit card and not pay it off for 8 years, which, by the way, is a horrible idea. So don't do that. But we're going to start off kind of the same way we did it before. We're going to say the present value, the amount that we're talking about right now, is $1,200. And whether you're investing or borrowing, the math is identical. It's just who owes who. Future value is what we're trying to find. How much we're going to have in 8 years, or how much she's going to owe in 8 years. The interest rate per compound period I is 20% per year, but since we're compounding quarterly, I'll divide that by 4. 20% divided by 4 is the same thing as 20 divided by 100 divided by 4, and that works out to be 0.05. N is the number of quarters of a year in 8 years, so that's really just 8 years times 4, which is 32. Okay, same equation as we were using before. Future value equals present value times 1 plus I to the exponent n. Our future value we don't know, so we leave it. Our present value is 1,200. This becomes 1.05 to the exponent 32. do the base to the exponent, then multiply by 1,200 at the end, and you should get $5,717.93. Okay, so Chantel borrows $1,200, and 8 years later she owes over $5,700. This is a good example of why you don't want to use credit cards and then not pay them off fairly quickly, because with high interest rates like that, the money builds up very fast. Question 5. Mike borrows $9,000 from Money Mart, which is a payday advance company, to buy a used car. The loan is for 5 years at 38.744% interest per year, compounded biweekly. How much will he owe at the end of 5 years? Now, this number in particular happens to be accurate. This number is actually what Money Mart charges. I'd feel bad about using an actual company in this example, except that this is their real current interest rate. Now, just in case anyone is Googling it right now as we speak, it may have changed from the time I posted this video. And even if you Google it right now, what you'll see is a slightly different number. It's actually higher than that. It's based on the fact that they technically compound annually, based on their annual interest rate. So the annual compounding is a little bit higher, which it works out to the same amount of money in the end. It's just that we use a smaller interest rate to compound more often than a larger interest rate to compound less often. But this is equivalent to their current real rate. So we get a $9,000 car. I don't know if anyone's been shopping for cars recently, but that gets you something mediocre, not something great. Let's see how much Mike's going to owe for this in the next 5 years. So the present value of the money he's borrowing is $9,000. The future value is what we're trying to find. The interest rate I is going to be 38.744% divided by 26, since we're doing it biweekly. Now this one unfortunately does not work out totally nicely in your calculator, because again, it's a real number from real data. It works out to be 0.0149, and we could keep going on. I think it's 0.158 after that, but we'll round off to 3 significant digits, and we will talk at the end of this lesson about what happens if you round this number off too much, especially over long periods of time or with high interest rates. Anyway, that's good enough for us for now. And the number of compounds is 5 years, 26 times a year, which is a grand total of 130 biweekly periods. All right, so future value equals present value times 1 plus I to the n. That's $9,000 times 1.0149 to the exponent 130. And when you plug that in, you'll get a number when you do 1.0149 to the exponent 130, multiply that by 9,000, and it works out to be, I believe it was 61,555.28. A little over $61,500 in 5 years on a $9,000 purchase. That is an incredible rate. Now, I will, in defense of Money Mart, not that I want to defend them, but I will slightly defend them, is that you're not intended to borrow the money for 5 years and then pay it back all at the end. You're expected to pay back little bits constantly every other week, which will definitely cut down on the amount of interest that you pay, but it's still this nasty interest rate that you never, ever want to get yourself into, because this money grows up way too fast. If you need to borrow $9,000 because you don't have $9,000, chances are in 5 years you're not going to have $61,000 or $62,000 to pay back. So do not get caught up in these interest rates. By the way, that was with our approximate value of I, which we rounded off. If you actually had left this part here in your calculator as an exact value, so 0.0149011538 something, you actually as a final answer would have gotten $61,567.41. So that's the exact value. This was the rounded I. So close enough. We're off by about $12, but I think that's pretty reasonable on an amount that's over $61,000. Okay. Now, sometimes we're going to go backwards. We want to know how much we're going to have or how much we're going to owe at the end, and we want to figure out how much that's equivalent to now. So for this particular example, um, Sky has some money now that she wants to set aside um, some of so she can take a trip to France in 3 years. Her investment will get her 13% a year compounded annually. That's a pretty good interest rate. And if she wants to have $7,000 for her trip, how much does she need to set aside now? So obviously the number should be less than 7,000. Maybe it's 5,000 or 6,000 she needs to set aside, and after 3 years it'll build up to 7,000. So we do this pretty much the same way we did the others. The only difference is now we don't know what the present value is. We know the future value, the amount we're going to have later, is $7,000. Interest rate is 13% a year. And because it's compounded annually, we don't have to worry about dividing by anything. So this is just going to be 0.13. And N is 3 years. Again, we don't have to worry about multiplying by anything here because it's once per year. Okay, so now we just use our equation again. Future value equals present value times 1 plus I to the n. And now in this case, we actually know the future value is 7,000. And the present value is the unknown. This part here will be 1.13 cubed. And we can simplify that just a little wee bit on the right-hand side. So what we're going to do is write this as 7,000 equals present value. 1.13 to the exponent 3 is 1.442897. That's probably more decimal places than we need, but what the heck. And then if I want to solve for present value, I'll just divide both sides by that number. So 7,000 divided by 1.442897. And what that ends up being, once I do the division, is $4,851.35. So Sky wants to go on vacation in 3 years. She doesn't have to set aside the $7,000 now. She only has to set aside $4,851, and that will have grown to $7,000 within the 3 years. Not too bad. All right, example 7. How much money must your save invest now at an interest rate of 9% per year compounded monthly if he wants to have $20,000 10 years from now? Okay, so his future value, the amount he's going to want later, is $20,000. The amount that he needs to put aside now is what we're looking for. We don't know what it is. The interest rate is 9% and it's compounding monthly, so we'll divide that by 12. 9% divided by 12 is 0.0075. And the number of compounds is, again, the number of months in 10 years, so 10 times 12 is 120. So we set up our equation. Future value equals present value 1 plus I to the exponent n. Future value is going to be 20,000. Present value we don't know, so we leave it. 1.0075 to the exponent 120. Now the only thing we can really do in this step is do our 1.0075 to the exponent 120. This works out to be 2.451357. You'll notice I keep a fair number of decimals. I don't like rounding off in these equations because it can cause errors later. And then I'm going to divide both sides by that number. Oop. My dyslexia is showing. All right, and once we do that division, it works out that we have $8,158.75. And by the way, I kept all the decimals in my calculator for the value of 1.0075 to the exponent 120. So it had a couple more decimal places. So if you're off by a few cents or even a few dollars on this one, it's just a rounding difference. I just have that 2.45 number precisely in my calculator. Okay, so Gersave only has to set aside a little over $8,000 now so that he'll have $20,000 in 10 years. Not too bad. All right. I thought I'd throw this in just to be clear about what happens when we do rounding. This is based on an actual episode of Futurama, and I thought the math in it was interesting. When I saw the episode, I'm like, oh, is that real? I need to check that. So the character basically is frozen in a cryogenic chamber in the year 2000 on New Year's Eve, and he wakes New Year's Eve in the year 3000, 1,000 years later. And in one episode, he's constantly talking about how broke he is. And then he goes to the bank and finds out he only had 93 cents in his bank account. However, it has been gaining compound interest for the last 1,000 years at 2.3% interest per year compounded monthly. I will point out 2.3% is fairly high for a bank interest rate on a regular account, but it's actually relatively low for any other kind of investment. So it's a perfectly reasonable number to actually use. And so when we do this, we figure out that our value for I, the interest rate per month, is 0.023 divided by 12, which is 0.0019166666 repeating. So if we set up the equation for it, our future value is just going to be equal to our present value, 0.93 times 1 plus I to the exponent n. And in this case, n is 12 times a year for 1,000 years, or 12,000. So what I'm going to do is I'm going to actually just answer this question 4 times. I realize it seems like overkill, but trust me on this, you'll see why in a second. And what I've done is I've rounded it off a little bit. So I've taken the 0.00191666, I've rounded it off to one significant digit, 1.0019 rounds off to 0.002. And if I plug that into my equation for future value, I'm not going to bother doing the whole equation again over and over, but the future value that I get on this is going to be our 93 cents becomes 24,051,453,283. So Fry is then incredibly rich with $24 billion. Now, I will point out that we did round up a little wee bit on the interest rate. Not too much though. I mean, literally rounded 1.91 to 0.0019 to 0.002, which is fair rounding. But that gave us 24 million. Now instead of that, I'm going to keep 2 significant digits. I'm going to keep the 1 and the 9. The one after that rounds down. So 0.0019, which looks like it's pretty close. When I do the calculation on that one, the future value works out to be 7,261,096,621. So that slight rounding difference, a very, very slight rounding difference, is the difference between Fry having $24 billion and just over $7 billion. That's a pretty big difference. It's literally a difference of over $16 billion. So that's kind of huge. So maybe we should keep 3 significant digits and see what happens. 0.00192. The future value on that one, when we plug it in, works out to be $9,226,440,607. So note that just keeping that one extra digit, instead of 19, we went 192. That gave us another $2 billion in our bank account, just that third digit. And if we keep it exact, and when I say exact, I mean I just put the original number in my calculator and didn't round it off, we get the most accurate answer, which is closest to the true answer that we'd have, which is 8,865,345,638. Okay, which is not a big deal, but it is still like, 300 and almost $400 million less than the answer I get with 3 significant digits. So I think you can see that it is kind of important that we don't round off the I too much. If we round off one of the other numbers, it's kind of proportional. If we lose 5% of our number when we round off, we'll be off by about 5%. But here, even rounding off slightly with the I causes a pretty dramatic difference between results. So hopefully that kind of made sense. That's how compound interest works. You should be able to answer compound interest questions at this point. Good luck.